kinematics and projectile motion. So we have a steel ball held 40 centimeters above the table. It is released, and we measure how long it takes to hit the table. Calculate the time it takes for the ball to fall to the table. So a typical kinematics problem where we have an object, in this case a ball, traveling some distance due to the acceleration due to gravity. Before we start though, we need to define which way's up. What I mean by that is we need to define a positive direction. I will define up as positive, and I'll just draw an arrow like that, just so I'm very clear. That means any vector acting down will be negative. So let's have a think. What do we already know? Well, we know that the ball is traveling down 40 centimeters or 0.4 meters. So our distance, or rather our displacement, because it's a vector, is negative 0.4. Once again, because I defined up as positive, my distance will be negative 0.4. If you did it the other way, your distance would be positive. All right, and that's fine. What else do we know? It is released. Could we assume that the initial velocity is 0? Yeah, I think that's a fair assumption. They should have said it is released from rest, just to be a bit more specific, but we can definitely assume that. So VI for initial velocity is 0 meters per second. We don't need a positive or negative here. What else do we know? In the vertical direction, right, because we're just dropping it straight down, we know acceleration due to gravity is 9.8 meters per second. Again, this acceleration is acting downward, so we will have a negative. That is 3 known parameters, and we are looking for time, so we're in a good spot. To solve a kinematics equation, we need 3 knowns to find 1 unknown. So looking at our formula book, we find the equation that has these 3 knowns and 1 unknown. I'm just looking at it, and I see D equals VIT plus half AT squared, having all of those parameters. And now we can substitute in the values and solve for the unknown. So N for D, negative 0.4, VI is 0, so 0 times T just becomes 0, right, which we don't need to write, but I will just to show the step. 0 times T plus half A is negative 9.8 T squared. So we've substituted in the values. I'll just bring it over here. So we have negative 0.4 equals negative 4.9 T squared, right? Half times negative 9.8 is negative 4.9. I will divide both sides by negative 4.9, which is, menu run maths, 0.4 divided by 4.9, 0.0816. So T squared equals 0.0816, whatever that was on our calculator. And to find T, our last step would be to square root. So shift, square root, shift, answer, to take our previous value, execute. Gives us T equals 0.29 seconds. And if we were being completely correct, we would round it to one significant figure, because the distance is only to one significant figure. So we could also write this as 0.3 seconds to 1 SF. Awesome, and so that is an achieved question. Definitely on the harder end of the achieved scale, because we had to use the quadratic equation for distance. However, it simplified a lot, because initial velocity was 0 and we were left with T squared equals some number. Square rooting gave us the final time. So that's the time it will take this ball to hit the table, given it is accelerating down at 9.8 meters per second squared. Now, throwing one ball on a table is not fun enough, so we did it with another ball of the same size but half the mass. So let's ignore air resistance, explain how the time for the second ball to fall compares to the first. So I'm hoping you've watched the video of the feather and the bowling ball in a vacuum, and how they actually fall at the same rate, at the same speed. If you haven't seen it, look it up. Ball and feather in vacuum. And that's because they are both accelerating down at 9.8 meters per second squared. So like here, both balls are accelerating down at 9.8 meters per second squared. Right, and we are assuming both balls are dropped on Earth, right? We're not taking the table and the ball to another planet. And what this means is that they will have the same time to reach the table. And just looking at your formula sheet, looking at all the kinematics equations, you'll notice none of them have mass in them. In other words, they are independent of mass. Mass has no effect on its path. The only thing that affects its path is its initial speed, its acceleration, its distance, its final speed, and time. Now, the side note here is if we couldn't ignore air resistance, then depending on the shape of the ball, right, we would expect different times for it to hit the table. Just like you drop a feather versus a pen, the pen accelerates faster due to it's more aerodynamic, whereas the feather has a greater surface area, so more drag. But these 2 points would result in a merit for that question. Alright, so we haven't had enough of this ball on the table, but this time we are firing it horizontally, right off the edge, and then it's going to still accelerate down. However, it had some horizontal speed, so its momentum will carry it to the right as well. So what are we given? We're given two distances. We can still assume acceleration because we're on Earth, and we will define up as positive. But now, since we have two directions to deal with, we also need to define our horizontal direction, which one's positive, so I'll define to the right. Again, you could define it exactly the opposite to me, and you'd still get the same answer if you're consistent. Part 1, calculate the ball's final vertical velocity. So what direction are we working in? The vertical direction. So I'll just remind us by drawing my vertical arrow, up being positive. We are looking for the final velocity, VF. Looking for VF. In the vertical direction, what do we know? Well, we know it's accelerating down, so negative 9.8 meters per second. We were given the height of the table, so it's traveling a distance down of 0.7 meters, right, converting to SI units. Okay, that's two knowns. We need one more in order to solve for it. This one's a bit hard to see, but we can assume the initial vertical velocity is 0. In other words, when it rolls off the edge, we're not pushing it down with some extra speed. We're just letting it fall off the table with no additional initial vertical speed. Yep, and we don't know time, so we don't have that. So these are the only other three available to us. 3 knowns, 1 unknown. We can pick our equation and then solve. Looking at the formula sheet, I see VF squared equals VI squared plus 2AD, linking these 4 variables. So we can substitute in the values and solve. Looking for VF, so VF squared equals VI squared. Well, VI is 0. We square that. We add to that 2 times acceleration times, I'll catch myself here, distance. The ball travels from up high down to the ground. So according to my coordinate system, it should be negative. Like so. Now we can simplify. 0 squared is 0. Don't need to write that. And then the rest. 2 times negative 9.8 times negative 0.7, 13.72. Now is that our final speed? Nope, that's VF squared. Our last step is to square root. So shift square root, shift answer, 3.7 meters per second. And what would the direction be? So a reminder, when you square root a value, you actually get a positive and a negative answer, right, mathematically. However, in physics, we need to say, all right, what's the direction? Well, its final speed is definitely going to be down because it's been accelerated down. So we would either write 3.7 meters per second down, or we could put a negative out the front. And according to my coordinate system, negative 3.7 meters per second means 3.7 meters per second down. Right? They are the same thing. So I'll just put my down in brackets. All right, and your diagram doesn't hurt to just label that as well. All right, and so far that is achieved because we've calculated an unknown parameter using a kinematics equation. But to get merit, it's combined with part 2, and that is, what assumption have you made? So, a few assumptions. The main one is, in kinematics, we assume there are no external forces. So that means things like friction, air resistance, drag. The acceleration is only caused due to the gravitational force. Cool. And having that assumption with the correct calculation would be a merit. And it's not in the mark scheme, but an assumption we did make was that the initial vertical velocity was 0. And from the question, it's not entirely clear, right? There could have been a little bump at the end of the table, which meant it moved up first. It's having some vertical velocity up, or we could have knocked it off. So that's another assumption that you could make. Right, but this type of answer, linking to external forces and acceleration only due to gravity, is very common for kinematics because that's the main assumption. And finally, question D, calculate the size and direction of the velocity of the ball just before it hits the ground. Right, like as it hits the ground, basically. And they've given us a nice hint to first find the horizontal velocity of the ball. So, back to the diagram. We've already found the vertical velocity, right? Vf. However, to find velocity, we need both the vertical and horizontal components, because if we have that, so Vx and Vy for in the y direction, like vertically, we can find the resultant vector using vector addition, and that vector is v, its final velocity. So once more, that blue arrow Vy, we've already found, that's 3.7 meters per second down. The green arrow, we know actually from the question that it should be 4.8 to the right, but we need to show that. And once we've done that, we can then use vector addition to find the magnitude and the direction of the red arrow, v or Vf, right? Its final velocity. So let's go about finding Vx first. So we need to work in the horizontal direction, and I've defined to the right as positive. So what do we know in that direction? Well, we know the distance is 1.8 meters. What else? The acceleration, that would be 0. And why is that 0? Going back to our assumption that we made, the only force acting on it is the gravitational force, so the acceleration horizontally would be 0 because there are no like resistive forces, right? And the ball doesn't have like a thruster attached to it, right? So there's no left and right forces, so its acceleration would be 0. Okay, what else? That's only 2 parameters. How many do we need to solve a kinematics equation? We need 3. Do we know the initial velocity? Nope. Do we know the final velocity in the horizontal direction? No. In fact, they would be the same, right? Because acceleration is 0, so it wouldn't change. So we don't know Vi or Vf. So the only thing left is time. Do we know time? The time it takes for it to go from the edge of the table to hit the ground. We do not know time. However, we can work out time in the vertical direction, where we have more information, and then bring that into the horizontal direction to solve for V. So let's do that. So in the vertical direction, up being positive, we know distance, what was it, negative 0.7 meters, I believe. Yep. We know acceleration as negative 9.8 meters per second. Initial velocity was 0, and we actually worked out the final velocity, Vf, negative 3.7 meters per second. Right, negative meaning it's acting down. And so we have 4 parameters, which is more than we need, and we're solving for t. So we can look at our formula book, and we see that we could use any of these 3 kinematics equations. Right, so we do have quite the selection because we have 4 knowns and we only need 3. The mark scheme goes for this one, but let's mix it up and go for the last one because that looks easiest to me. So this is the one I'll go with. But again, all 3 should work. So I encourage you to try all 3 and solve for t in each instance. So let's do that now. So substituting in what we know, Vf is negative 3.7. Vi is 0, plus a times t. A is negative 9.8 times t. Solving for t, well, 0, we don't need to worry about that, so I'll just get rid of that. And to get t, we will divide both sides by -8. So t equals -3.7 divided by -9.8, which gives us 3.7 divided by -9.8, 0.38 seconds. And so that's our time. And again, what we're trying to find is the final horizontal velocity. So taking that time now back into the horizontal direction, we have three knowns, d, a, and t. We can solve for v. Right, again, vi equals vf because there is no acceleration. So you could either use a kinematics equation or the standard speed is distance over time, where this only works because acceleration is 0. Distance is 1.8 divided by time, giving us 1.8, and I'll use divided by answer, right, the unrounded time, which gives 4.8 meters per second. Awesome. So far we have started in the horizontal direction, realized we don't quite have enough to work out the final velocity, went into the vertical direction to work out the time it takes to hit the ground, take that back into the horizontal direction and worked out velocity as being 4.8 meters per second. Okay, and so what does that give us? That so far we're only at achieved by showing this. To get merit and excellence, we now need to take that and then find the resultant vector, right, the final velocity. So let's use a diagram first. We know, what is it, 4.8 meters per second to the right is its final horizontal velocity, and we know it's 3.7 meters per second down is its vertical velocity, and we are looking for its resultant, right, its combined velocity. Right, and to do this we use vector addition, and you'll recall from last year, Pythagoras' theorem, we can find the magnitude by squaring each side, adding them together and square rooting it. So the magnitude would be 4.8 squared plus 3.7 squared, all square rooted. 4.8 squared. So here I should actually be using the unrounded answer. So shift answer squared plus 3.7 squared, and then I will shift square root that answer, which gives 6.0 meters per second. Now that is the magnitude, but for a vector such as velocity we also need its direction. So to find the angle, we first label it on our diagram, and so tan of the angle is equal to opposite, so opposite the angle is 3.7 divided by adjacent is 4.8, and so the angle itself would be the inverse tan of 3.7 divided by 4.8. So we go shift tan 3.7, so in brackets, divided by 4.8, close bracket. Now, that looks wrong, right? Maybe? What do you think? So it's not wrong, but it would be in units of radians. 0.66 radians. And so you're probably more used to angles in degrees, and that's fair. So when you enter an exam, your calculator is reset and its default unit for angles is radians, but we can change that if you'd like. Shift menu to set up and scroll down to angle, change it to degrees, F1, exit, and we'll try that again. Shift tan 3.7 with brackets, 3.7 divided by 4.8, close bracket, 37.6 degrees. Right, equivalently. And now that is sufficient because we have drawn a diagram showing what that angle means. But you could, if you'd like, work out the angle from the horizontal. Is usually a bit more common, which would be, what would that be? 90 minus that, 52.4. No, what am I saying? They would be the same because they are, alternate angles and parallel lines. Anyway, let's not revise our Year 9 geometry. What matters here is that we have drawn a diagram, we've labeled an angle, we've calculated its value, and we've also calculated its magnitude. Right, answering the question fully. And that would be excellence. If you made a minor mistake with either of those, it would be a merit. Right, that's it from me for today. I'll see you next time.